Hello everyone, my name is Kexin and I'm today going to present my master thesis, and the study is about dynamic response patterns and safety implication of e-scooter riders in hazardous scenarios, a group-based trajectory modeling approach. And the content will be followed as this 5 part. So the first part is about the introduction. So in recent years, e-scooter has become one of the most widely used shared micromobility modes, especially in North America and Europe. And so as we show on the left, shared micromobility ridership has grown rapidly, and the e-scooters now account for more than half of the shared micromobility trips in US and Canada. But however, this rapid growth has brought increasing safety concerns. Evidence shows that emergency department visits associated with micromobility product increase sustainably. Compared with bicycles, e-scooter riders have higher emergency percentage rate per million miles traveled. And among different crash types, interaction with motor vehicles are especially critical because of the large difference in the mass and speed. Collision between e-scooters and motor vehicles can lead to severe injuries. So studies in Nashville and Sweden show that motor vehicle collision are an important component of serious and fatal e-scooter crash. Therefore, understanding how e-scooter riders as a vulnerable road user group respond in other interaction with motor vehicles is important to improve this vulnerable group safety. So, although e-scooter safety has increased attention, as we mentioned on last page, existing studies still provide limited understanding for riders' dynamic hazard response. So first, most hazard reaction research has focused on car drivers, and some studies has examined traditional two-wheelers. However, e-scooter riders remain relatively underexplored. This is important because e-scooter riders are directly exposed to the traffic environment and has no vehicle body protection. So their perception, judgment, and control response can strongly affect both crash occurrence and injury severity. In addition, findings from traditional two-wheelers such as bicycles and motorcycles cannot be directly transferred to e-scooters compared with previous traditional two-wheelers. E-scooters have several unique features such as smaller wheels, standing posture, weaker stability. So this characteristic may lead to different control behaviors in hazardous situations. And moreover, recent e-scooter studies found out that most mainly focus on post-crash outcomes, infrastructure, policy, or general safety issues. The studies are valuable, but they do not fully explain what happens before a crash, such as how riders perceive hazard, adjust speed, and control the vehicle. Therefore, there is limited evidence on how e-scooter riders respond to hazard and how the response relates to crash mechanism. Hazard response are not fixed or uniform. They may vary across from rider scenarios and vehicle types. As for rider level, factors such as experience, ability may influence how a rider judge and respond to risk. At the scenario level, conflict structure and vehicle approach direction may change the available avoidance strategy. Vehicle attribute and dynamics may also influence the hazard response. Many existing hazard response studies started from car driver behavior and have mainly focused on car drivers. For car drivers, braking is often considered as the most direct and common avoidance response. Therefore, many current hazard response studies rely on longitudinal control, which speed control variables may braking reaction time, PTTC threshold. However, this framework is not directly applicable to two-wheelers, including e-scooters. Riders may need to use steering, lateral avoidance, or combined speed and steering control. Previous studies have found out that braking capability of e-scooters may be limited, making the lateral avoidance more important in some close-range conflicts. Nowadays, some two-wheeler studies has started to consider steering-related response. However, many of them still analyze the speed and steering indicators separately, or use static categories such as braking only, steering only, and combined response. This approach do not fully show how speed regulation and horizontal control evolve together over the time. So therefore, this study argues that e-scooter hardware response should be modeled as a joint process of speed regulation and horizontal control rather than braking or steering only. So to study the dynamic hardware reaction, this study needs to satisfy several requirements. So first, it should preserve the temporal reaction process because riders' behavior change continuously during the conflict. Second, it should identify reaction heterogeneity, like the difference of the reaction, because riders or events may show different response patterns. Third, the result should remain behaviorally explainable. Finally, for this study, the method should be capture the joint control process between speed regulation and horizontal control. So at present, the traffic safety and driving behavior studies mainly use 4 types of method: traditional statistic method, past modeling, clustering method, and deep learning method. These methods are useful for testing group difference, explain variable relationship, identify response tendency, or predicting behaviors. However, they still have limitations for dynamic hardware reaction analysis. Many of them rely on aggregated indicators such as mean speed, maximum. This may lose temporal information because the same aggregated value may correspond to different trajectories. So in addition, deep learning methods may achieve high predictive accuracy, but their behavior interpretation is often limited. Therefore, this study used GBTM and joint trajectory modeling to preserve 4 reaction trajectories, identify latent reaction groups, and maintain behavior interpretability. So based on the previous discussion, there are 3 main research gaps. First, existing e-scooter studies provide limited evidence on riders' dynamic hardware responses, especially before a crash occurs. Second, current hardware response research still relies heavily on longitudinal control indicators, while the joint evolution of speed regulation and horizontal control has not been sufficiently examined. Third, commonly used methods often rely on aggregated indicators or black box prediction models, which makes it difficult to preserve temporal process and maintain behavior interpretability. To address this gap, this study used a VR headset and a 4-axis scooter simulator to reproduce hardware interaction between e-scooter and motor vehicles in a controlled environment. Mathematically, I use GBTM and joint trajectory modeling to identify joint speed horizontal control reaction patterns. I then relate this reaction pattern to hardware scenarios scenario structure and PTTC-based safety outcome. Accordingly, this study asks 3 research questions. So first, what joint reaction do riders exhibit? Second, how do these patterns different across hardware scenarios? Third, to what extent are these reaction patterns associated with safety risks? In terms of practical significance, this study can provide insight for rider safety education and targeted intervention and e-scooter driving assistance. And as for nowadays commonly used AV driving assistance, if you know the other part behaving pattern could help the system to better make the operation ideal. So based on previous e-scooter crash data studies, we select 4 frequent crash types and converted them into experimental hardware scenarios. In scenarios, the e-scooter riders travel straight. The 4 scenarios include 1 vehicle turning conflict, 2 crossing conflict, and 1 rear overtaking conflict. To ensure comparable conflict urgency across participants and scenarios, we designed a trigger-based conflict control system. When the rider enters the trigger zone, the system extracts the rider's current direction and speed. Based on the based on the PTTC threshold, it automatically calculates the interacting vehicle entering timing and speed. In this way, the harder vehicle enters the scene under controlled conflict urgency, while the rider's response remains naturally. We used a simulated Korean city environment as the experiment setting, which was built in Unity and connected to the VR headset and the 4-axis scooter simulator. To reduce VR-related discomfort, instead of one long continuous ride, we divide the experiment into 3 5-minute ride routes. Across the route, each participant experienced 8 harder events, and each of the 4 harder scenarios appeared twice. In total, 34 participants took part in this experiment, and 2 participants were excluded because of the severe VR sickness, resulting a final sample of 32 participants, and including 19 males and 13 females aged from 23 to 35. After obtaining the experiment data, we first conduct data pre-processing to clean and organize the data set. The first step was invalid event removal. After removing 280 valid hazard interaction events remain for analysis. Next, all events were aligned based on the closest approach moment, which is the time when the rider and the hazard agent reach the minimum distance. This allowed events with different duration to be normalized onto a common event progress axis. Then, stage-specific windows were constructed for feature extraction. The extracted features including speed response, horizontal control, visual scanning, and safety margins indicators. Finally, a multi-collinearity was checked before these variables were used in the trajectory modeling and safety analysis. Now I will introduce one of the main methods used in this study, group-based trajectory modeling, or GBTM. GBTM has widely used in the medical and public health research to analyze longitude patient data and identify different evolution patterns among patients. In this study, GBTM treats the observer indicator trajectories as a finite mixture of several latent trajectory groups. Each group has its own trajectory shape and group proportion, and each event is assigned to the group with the highest posterior probability. But GBTM is used to identify trajectory groups within each single response dimension. This study aims to investigate joint speed horizontal control reaction. Therefore, I further use the joint trajectory modeling, which is an extension of GBTM. Based on the GBTM result, the joint model links speed and horizontal control trajectory groups by estimating the probability of each group combination. Each event is then classified into the most likely joint reaction patterns. In this way, the model combines speed trajectory groups and horizontal control trajectory groups to identify the final joint reaction patterns. Here, I refer to a causal model from previous traffic conflict research to clarify the analyzed logic. So from GBTM and joint trajectory model, we obtain the reaction patterns. However, their relationship with the safety outcome is still not clear. Therefore, I adopted a Bayes framework, including a mixed effect model and a set of model comparison. The mixed effect model focuses on the downward relationship from the reaction to outcome. This part aimed to answer one question. After controlling for the initial condition, do different research groups still have different PTTC-based safety outcomes? In the model, HS and reactions are treated as a fixed effect, while participants is included as random intercept. The model comparison focuses on the relative contribution of this source. These two, the two downside arrows. To better understand the predictive contribution of each source, I considered two measures, marginal contribution and interdependent contribution. And for here, all comparison models are modified versions of the mixed effects model. For example, if we test the single source contribution of HS, then only HS fixed effects is retained in the model. But if we test the independent contribution of HS, we compare the full model with a reduced model that excludes hazard scenarios. So now for the results, here are the GBTM results for selected dynamic indicators. I will explain detailed about the trajectory pattern later. This important part is that the speed mean, which I will call SM, and horizontal input were used as the two main dimensions for joint trajectory modeling because they represent speed regulation and horizontal control. SA, which is the cascade frequency, as it will be retained as a supplementary perceptual indicator, which help us to better understand the visual scanning characteristic behind some reaction patterns. So this is the joint model result for speed and horizontal input rate. The patterns are quite similar to the single GBTM result. So for speed mean, the three groups are in class 1 shows a continuous speed reduction, class 2 shows a speed adjustment and recovering pattern where riders first slow down and then recover their speed. Class 3 shows a high and stable speed patterns. So for horizontal input, the three groups represent low, moderate, and strong horizontal control input. By combining these two dimensions, the joint model identified different speed horizontal control reaction patterns. The most frequent reaction pattern was SM3HI1, accounting for around 32% for all events. It's quite interesting finding because many riders maintain high speed with low horizontal control. And I will go back to this group later. And the next two major groups were SM2HI1 and SM3HI2, which accounting for about 22%. SM2HI1 reflects the speed adjustment with low horizontal input, while SM3HI2 reflects high speed with moderate horizontal input. Based on the identified joint reaction patterns, I then look backward to examine how these patterns are distributed across hazardous scenarios participants. The hazardous scenario level, the association between HS and reaction is statistically significant, with P less than 0.001 and Commerce V around 0.53. This suggests that a strong association between scenario structure and joint reaction composition. Looking at the enriched cells, HS2 is strongly associated with SM3HI1, and HS2-3 is mentally associated with SM2HI1, accounting for 51.6%. And HS4 is mainly associated with SM3HI2. This means that different scenarios tend to lead different speed horizontal control reaction patterns. Also, for the heat map, we can first see that the reaction composition difference occurs the four hazardous scenarios. Different hazardous scenarios show different reaction composition. Even when two crossing scenarios look similar, like HS2 and HS3, which are both crossing conflicts, their reaction proportions are still different. At the perception level, this result also show how some rider level different. On the average, the dominant reaction accounts for around 50% of the participant events, and the top two reaction account for 75%. The total variation distance is 0.456, suggesting that some participants' reaction profiles different from the overall sample distribution. So now I take two safety outcome indicators into consideration. So it's mean distance and mean. Here, mean distance is used to describe spatial proximity, while mean PTTC is used to describe the temporal safety margin. From the value highlight, we can see that different hazard scenarios have different safety contexts. For example, hazard scenario 1 has relatively low mean distance and low mean PTTC, which means it both spatially close and temporally urgent. Hazard scenario 4 shows a higher mean PTTC, suggesting that a large temporal buffer, but not in distance. So this means that HS hazard scenario itself already provides different spatial and temporal safety conditions. Also, spatial proximity is not always consistent with temporal safety margin, as we can see from the hazardous scenario 3 and hazardous scenario 4. Therefore, I further focus on mean PTTC to examine the temporal safety outcome in more detail. The heat map shows the mean PTTC for each hazard scenarios and reaction group combination. We can see that the mean PTTC different not only across hazard scenarios but also across joint reaction groups within each hazard scenarios. For example, SM2HR1 shows relatively high PTTC in several hazard scenarios, but much lower PTTC in hazard scenario 1. This means that the safety meaning of a reaction pattern is not fixed. It depends on the context where the reaction occurs. Previously, we found that SM3HI1, the high speed and low horizontal input grade, was very frequent, especially in hazard scenario 2. This is an interesting result because it means that many riders maintain speed and did not turn during the hazard interaction. To better understand the reason, I further used cascade frequency SA as a perception indicator. Here, SA1 represents the low cascade group, while the SA3 represents the high cascade group. I mainly compare the HS2 and HS3 because the two scenarios had a relatively high proportion of high-speed straight-through response. The result shows that in both hazard scenario 2 and hazard scenario 3, the low cascade group showed lower mean TTC and shorter mean distance than higher cascade group. In HS3, SA1 had a mean TTC of around 0.9, while SA3 had a higher value of 0.12. The same pattern is also observed for mean distance. This suggests that some high-speed straight-through response may be related to limited visual scanning and weaker hazard perception, especially in the crossing scenarios. So in other words, some rider may not have fully recognized their hazard early enough, so they maintain a high speed and low adjustment response. So this slide represents the base model result for PTTC-based safety outcome. The analysis has two parts, the mixed effect model and the model comparison. First, the mixed effect model examines whether different reaction groups still show different PTTC after controlling for hazard scenario and participants. The outcome is log transferred mean TTC. Here, the most frequent group is SM3HI1 is used as a reference reaction group. The result shows that SM1HI1 has around 30% lower PTTC than SM3HI1, suggesting a smaller temporal safety margin. In contrast, SMI1 and H3 and SM2HI1 show higher PTTC with increase of around 160% respectively. For other two reaction patterns, the credible intervals include 0, so their differences are not clearly identified. Second, the model comparison evaluates which source contributes are more to PTTC prediction, hazard scenario reaction or participants. Here, the ratio is calculated as delta ELPD divided by SE, and a ratio greater than 2 suggests a clear predictive improvement. The result shows that the hazard scenario has the strongest contribution with the highest margin and independent ratios, and the highest Bayes R square. Reaction also provide additional predictive information, while participants play a supplementary role. So overall, the PTTC-based safety outcomes are mainly structured by hazard scenarios, but joint reaction patterns still provide additional behavioral safety information. So to summarize, this study has 3 main findings. First, hazard scenes themselves provide a safety risk context. The Bayes model comparison shows that the hazard scenario has the strongest predictive contribution to PTTC, with a Bayes R square of 0.5. This suggests that the scenario structure is a major source of safety variation. Also, distance and temporal conflicts are not equivalent. For example, we can compare HS1 and HS2 shows that a large spatial distance does not necessarily mean a large temporal safety margin. So second, HS is strongly associated with joint reaction patterns. The HS reaction associate is significant with P less than 0.001 and the comma V around 0.53. This means that different scenarios tend to produce different speed horizontal control reaction patterns. For example, the difference between HS2 and HS3 suggests that vehicle approach direction matters. HS1 is more associated with mixed reaction involving deceleration and horizontal input, while HS4 shows more horizontal control related reaction. Third, the joint reaction pattern also provides the safety-related information. The same reaction may show different mean PTTC levels across harder scenarios. Therefore, the reaction groups should not labeled as fixed safe or risky response. Overall, the HS defines the structure safety context well. Reaction as the behavior safety information within the context. The safety risks should be interpreted through the HS reaction combination. This study also has several limitations. The first, the sample size and sparse reaction groups are limited. Rider level modeling is still preliminary. Perception and cognition were not fully integrated into the core model, and the simulated results still need to validate in real-world riding. So the future research, we can increase the sample size and repeated events per rider and integrate perception, decision-making, and psychological indicators to better understanding the rider's decision and combine with field observation and naturally riding data. And it could be expanded to more urban micromobility conflicts. That's all for my presentation. Thank you.